Okay, so we're going to conduct a goodness of fit test. An obstetrician wants to know whether the proportions of children born on each day of the week are the same. She randomly selects 500 birth records and obtains this table shown to the left. The question that we're going to answer today is there reason to believe that the day on which a child is born occurs with equal frequency at the alpha equals 0.01 level of significance? Now, step one to this is to write the hypothesis and the null hypothesis. So, our null hypothesis would be that the probability of day 1 is equal to the probability of day 2, which is equal to the probability of day 3. Of course, day 1 being Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. But they all have the same probability. And that would be 1/7 because there's 7 days in a week. Our alternative hypothesis would be at least one of the proportions is different from the others. As we said before, the level of significance is, we don't want to forget that, 0.01. And that'll help us when we actually use our chi-squared table. So now we have to figure out, we have the frequency, we have the observed values, we have to talk about the expected values. Well, what we know is that there were 500 birth records obtained. 500 times 1/7 is 71.4. So we're going to use that in our calculation. And since all expected counts are greater than or equal to 5, the requirements for the goodness fit test are satisfied. So we need to talk about finding our test statistic, chi-squared. So to find our test statistic, we have to add, we have to do the summation of the frequency minus the expected squared divided by the expected. So, for example, Sunday there was 46 births, so it will be 46 minus 71.4 squared divided by 71.4. That's for Sunday. Plus Monday. Monday there were 76 births. 76 minus the 71.4 squared divided by 71.4 plus Tuesday, etc. Okay, so here we have Sunday, Monday, Tuesday, Wednesday. We would have to do this for Thursday, Friday, Saturday. And when we take our frequency minus the expected value, square it, divided by the expected value for everything, we add them all up, we do the summation. Our chi-squared is 19.568. And this is our test statistic value. Okay, now we're going to take the classical approach and we're going to have to go into our chi-squared table, and we have to talk about our degrees of freedom. Our degrees of freedom would be 7 minus 1 because there's 7 days in the week, minus 1, you always subtract 1, so we have 6 degrees of freedom. If you look, sorry, test statistic, if you look and on the chart and find your critical value for chi-squared at alpha equals 0.01 with a degree of freedom of 6, your chi-squared critical value is 16.812. And now what we simply do is compare our test statistic with our chi-squared. Okay, so again, our chi-squared critical value was the 16.812. Our test statistic, our chi-square test statistic, that we figured out was the 19.568. And what we do is we just compare that on n. Now this is not a normal curve, of course it is skewed, so that's why it's chi-squared. And if, let's say this was our chi-squared at 0.01, this is our 16.812, you can clearly see that your test statistic falls in the critical region. So because the test statistic, 19.568, is greater than the critical value, 16.812, we reject the null hypothesis. Reject the null, which is h sub 0. Therefore, there is sufficient evidence that at the alpha level of 0.01 level of significance to reject the belief that the day of the week on which a child is born does not occur with equal frequency.